pronounced Cauchy. And Cauchy did a lot of important things in mathematics. Many of the things he did are more important than the poles and residues idea, but the reason for talking about poles and residues is not particularly to do the problems in 8.4. It's much more that if you take the systems and circuits class in engineering, as you would if you're doing engineering, they use the poles and residues method in the circuit analysis. And also, if you take the differential equations class, you use poles and residues in the Laplace transform methods that are used in solving those. So what I'm doing today is more trying to prepare you to take other people's classes later. You will not really find anything about poles and residues in the book because you can do partial fractions other ways. And so anyway, if you look at something like the first problem in 8.4, they start with this fraction. And what you want to do is rewrite it as a sum of fractions which would have exactly one of these factors in each fraction as the denominator. The reason for doing this from the standpoint of this book and this class is then that if you can find the correct numbers here for A and B so that this would be an identity, then if you were trying to integrate this, you could say it's this integral plus this one. And you can see that these integrals, where A and B are constant, are natural logarithms, because dx, say you think of the A factored out, and you just have the integral sign, and then dx over x minus 3, the antiderivative for that is log of absolute value of x minus 3, or simply log x minus 3 if you're assuming x is bigger than 3. And the same would be true here. Think of factoring out b, whatever number it is, and think of dx over x minus 2, and then the antiderivative is log x minus 2. So the fractions where each one has a single factor in its denominator are what we call partial fractions, because if you get the correct numbers, they'll add together to give you this fraction. Okay, so partial fractions is something that a graphing calculator will do, and certainly something like Maple, Mathematica, MATLAB, and all of that. It's really, as far as just taking fractions and writing it in partial fractions, that much really is algebra and isn't calculus until you put the integral sign on it. So the way that they're selling in the book is perfectly true as far as it goes, and that is that this is supposed to be an identity when you get the correct numbers for A and B, true for all x other than where you'd be trying to divide by 0. So true for any x except 2 or 3. So therefore, you could choose a value, whatever x you like, other than 2 or 3, where you'd be dividing by 0, put that number here, and there, and there, and there, and there, and that gets you an equation with two unknowns, the A and the B, that you need to identify the partial fraction. Then you can take any other x beside the one you used, and 2 or 3, put that in, and you get a second equation in the two unknowns, A and B. And then you can solve two equations and two unknowns. Well, that's certainly easy enough to understand, and that's what the book's selling. The only thing wrong with that is that it's fine as long as you're talking two factors and two fractions and two unknowns. Well, how about if you have three factors? Well, then you got three equations and three unknowns. Well, that's harder. You can do it, but that's harder. But how about 4, 5, so on? That's not very good. If you have enough factors, it's beyond, well, 5 is about all your graphic calculator will handle, is about 5 equations and 5 unknowns. You get enough factors and you're beyond what a really good computer will do. However, the poles and residues method will work no matter how many factors you have, and isn't that hard to do. So that's why I'm trying to show you about it. Now, I won't do anything to force you to use poles and residues. I won't have a test where it would insist that you do something that way. But it is worth your while to get the idea, I think. So, we need a couple of definitions. What's a pole and what's a residue? And this terminology goes back to Cauchy, as I said and showed you with the handout. Cauchy was the French mathematician who coined these words and pioneered this method. Okay, so thinking of trying to find A here. The pole for A is the number for which the denominator is 0. So the pole for A is 3, and the pole for B is 2. It's the solution then that you get if you set the denominator equal to 0 and solve for x. So that's not hard to see. Okay, what's the residue? Well, to get A, what you do is say, as I have over here, why do poles and residues work? Say you're trying to get A, thinking of this same problem, multiply through everything by the denominator, as I did with the green colored factor. So when you do, you see the factor over here in the original fraction corresponding to the denominator of A will cancel out, and it will cancel here. So what it will leave you here is what you call a residue. The word residue in English means what's left over after something or other, right? And so the residue, if you're trying to get A, is what's left of this fraction, the original, after you've multiplied through by the denominator of A. So this is the residue, and it equals A plus the residue times all the remaining terms over here, no matter how many there might be. In this problem, there's just the one term, but you could have 50 terms if they're all fractions like these with different factors over here as their denominator. So you'll have the original denominator of A times however many terms there are. So then, when x is takes the value that is what we call the pole. In other words, when x is 3, you'll have 0 times all this, and it leaves you a equal to the value here at the pole, at 3. So the limit of the residue here as x approaches 3 will be a times the limit as x approaches 3 of x minus 3 times everything. So that's gone, and a equals this with a 3 put in, 15 minus 13 over 3 minus 2, which is what I've said here. A is the residue at the pole, so it's this fraction evaluated at 3, so it is 2. Now what I found is A, regardless of finding B or not. So what poles and residues lets you do is get the numerators of these partial fractions one fraction at a time. Whether you want the others or don't want them doesn't matter. If you do, you can repeat the game and get B, and if there were more factors and more fractions, you just keep going. So in principle, you could do this even if you had a large number of different linear factors like this. This is what you call distinct because the numbers here are different. Linear because they're first power factors. So we can get the pole of B then as 2. The residue is what's left if you have multiplied by x minus 2, so it's 5x minus 13 over x minus 3. People use the word suppress they would say that the residue for A, you identify the factor, it's the denominator of A, and cover that up like that. The residue is what you see. And then if you want the residue for B, cover that one up, and the residue is what you see. You can look at it that way if you want. And so pole B is 2, and the residue is what I have here, and then B is the value of the residue at the pole, so it's 3. So you can check, see, I'm saying now that 2 over x minus 3 plus 3 over x minus 2, if I add the fractions, will give me what I started with. So when you are trying to add or subtract two fractions, just cross multiply. So this times that, whatever the sign is, this times that, and then the denominator is the product of that one. That's math 25, right? And if you do this and do your algebra, you'll see it works. So obviously then, as I already said, the relation to section 8.4, or I guess it's 8.5 in the new book, is that if you put an integral sign on the original problem, you can do that on the partial fractions, and then this one will be, you would have 2 times log x minus 3, and here you'd have 3 times log x minus 2. So I forgot to write the 2 and the 3, didn't I? Well, so you really would have 2 times it, or it would be squared, and you'd have 3 times it here, or it would be cubed, like that. So again, as on why do poles and residues work, looking at it one more time, if you wanted A, you could multiply everything by the denominator of A and cancel over here, and when you do, you see what's left is your residue. That'll equal A, and then the denominator of A times everything else. And when you take your limits, here you'll get the 15 minus 13, so you get the 2 equals A, and here you get 0. And then in the same way for B, if you wanted it multiplied by x minus 2, and what remains here is the residue, and you'd have the x minus 2 times A, so, and then you'd have B. So at x equal 2, this will be gone, and the value here at 2 will give you the 10 minus 13 over the 2 minus 3, so you'll have minus 3 over minus 1, which would give you the 3. So for distinct linear factors, poles and residues is really pretty slick. If you have something else, you might have some linear factors repeated. You might have some distinct linear factors, and you might have quadratic factors. It's possible to prove in algebra that you can write any polynomial as a product of linear factors, possibly repeated, and quadratic factors. So everything that you would have to deal with is either linear repeated, quadratic, conceivably quadratic factors repeated. And so you can attack any of the situations with poles and residues. It may be, especially if you get the quadratic factors, as we will do here in a few minutes, you may feel that it's more trouble to work with complex numbers than it's worth. But at least for the linear factors, do that much with poles and residues and cut down how many simultaneous equations you have to solve if you're going to do it in a method that uses solving simultaneous equations to some extent. At least cut down how many variables. So I would say at least do poles and residues like this for the distinct linear factors, because that's pretty easy. And it's a lot easier to solve 2 equations and 2 unknowns than it is to solve 3 equations and 3 unknowns, or 4 equations and 4 unknowns, and so on. At least if you're doing it by hand. Now, if you're using machinery, it doesn't make any difference. It's just electricity. Okay. So, for instance, look at problem 3, where you have a repeated linear factor, as you see. When you have that, you have to allow for whatever is the linear factor to all possible whole number powers up to and including the one that appears in your original problem. So if this is squared, then there can be a fraction with x plus 1 that's first power and a fraction with x plus 1 that's squared. You'll see that that's true because we'll find the A and the B, And we'll end up seeing down here that the fractions that will add to give you this are here. There's a fraction with x plus 1, and there's another fraction with x plus 1 squared. So at the very least, I would start doing poles and residues. And you see, if you were doing the equivalent of what I was showing you here with why do poles and residues work, the idea is that to find these numerator coefficients, the a and the b, you multiply through by the denominator. Okay, so the question here is multiplying through by the denominator. Do you multiply through by x plus 1, or do you multiply through by x plus 1 squared? The answer is you multiply through by the repeated linear factor to whatever is the highest power you have it in the original problem. So in this one, you have x plus 1 square, so that's what you multiply by. And so what you're going to get then is the residue for b, and you think of the minus 1, where this factor is 0, as the pole for b. If this had been cubed, you'd have an a over x plus 1, a b over x plus 1 squared, and a c over x plus 1 cubed. And then you'd be after c to start out, and you'd be multiplying through by the factor cubed, and so on. So my residue for b, if I've multiplied by the x plus 1 squared, is the x plus 1 squared times the fraction here, so it's x plus 4. And my pole b is minus 1, so b is just like in this first problem, the residue at the pole. So you take your residue, x plus 4, put in your minus 1, and you get 3. So b is going to be 3, no matter what else you do. Now, to get a, then, if you want to kind of mix poles and residues with what the book's selling, which is always substitute for x and solve an equation for your numerator of your partial fraction as an unknown. Once you found that b is 3, you could take any x other than minus 1 and put it here and there and solve for a. For example, if you wanted to use x equals 0, which I did, you see, I've shown you if you use x equals 0, where it would go. And then what do you have? 4 equals a plus 3, so a would be 1. So that's a mix of poles and residues and substitution. But you can check that 1 for a and 3 for b work, because if you take 1 over x plus 1 plus 3 over x plus 1 squared, what you'll have then is these two fractions, and if you add the fractions, you see, if you get a common denominator, you're multiplying top and bottom here by x plus 1, and so then you'd have x plus 1 plus 3 and x plus 1 squared, and you see that's x plus 4 over x plus 1 squared. So you can see it works. Now, if you want to do it all by poles and residues, you'd start out the way we did, where we found that B is 3. So then if you were looking at this line, you could do this. Multiply by x plus 1 square, and so then you'd have x plus 4 equals a times x plus 1 plus the b, which is the same as 3. Whether you wrote b here or wrote 3 here wouldn't matter. Because what you could do is you could differentiate. You notice this was your original residue, x plus 4. So the derivative of the residue for b, which you see is 1, would be the derivative here, which would be the a. If you're thinking of this as x plus 1 to the first power, when you do the derivative, you'd have 1 x plus 1 to the 0 power, so it's gone. So you really have the derivative of your residue equals a plus the derivative of b, which will be 0. Whether you just called it b or called it 3 wouldn't matter. So there is a formula then that if you have a repeated linear factor, and it's repeated just the one time, so it's square, then you go for what would be the numerator of the partial fraction that has the highest power first by getting its residue, and then the derivative of the residue will be the numerator for the first power term. There's a pattern to it, so I'd write the derivative of the residue over 1 factorial. The reason for putting in the 1 factorial is that if this were cubed and you had 3 terms, you'd get your residue. Then for the square term, it would be the derivative over the 1 factorial, and then for the first power term, it'd be the second derivative over 2 factorial. So you can do it like that. We don't have any problems where there are cubes on the repeated factors, so, but I at least want to say what it is you do. Okay, so what we have with the original problem, if you were going to do an integral, then is the integral of dx over x plus 1, because a is 1, plus the integral of b, which would be the 3, x plus 2 to the minus 2 power. So I better put my 3 in there. See, we found that a is 1 and that b is 3. And so then you, with the minus 2 exponent, you add 1 and divide by the new exponent, and so you'll have minus 3. Oh, that one is very good. Yeah. You'd have minus 3 over x plus 1. So now look at, now let me give you some maple on this.